Okay, almost time. Oops. Okay, let's start this Friday afternoon lecture, and I guess then you're off for weekend. So, as see today we'll talk about transport level security. And these are the topics. We'll talk about web security in general first, and then we'll talk mainly about these two protocols, TLS and SSH, but we'll also mention some other protocols around it. But they are the two main things we'll talk about. And of course, of those, it's TLS that is connected directly with the web, but we'll also see some connection with SSH actually. So starting about the web, there are special concerns about web security, and these are some of the reasons why we have special concerns. First, it's visible. I mean, that's the idea with setting up web server, that people can access it, you have information. So it needs to be a system that is accessible from almost anyone. Of course, you could have an intranet, you could have closed web service, but that's not the normal situation. So that's unlike many other systems where you typically set them up inside an organization, only supports users on the inside, but this is different then. Secondly, a web server today is quite complex. There are lots of different technologies that is used in order to get a web experience that we want to have today, including connections to different databases. You have different types of dynamic content. It's dependent on what type of platform you're using. You have lots of connections with other systems on. So it's quite complex actually. So there are potentially a lot of flaws in it, of course. We know that any system typically have flaws, and the more complex it is, the more flaws. And a web system typically is built up with a number of modules that work together. And that again drives flaws more than if you have a big system that is built as a single system. To add to that, it's easy to start up a web server. You just download some web server and you start it, and then you're up and running. And you can start publish pages. But what you don't see is then that you really need to configure it. You really need to think about all the things that it's configured in a secure way. And that's easy to forget. So a lot of web servers are set up in a way that they are not secure. And users are not aware of risk, both the ones that is setting them up, but also users of the web server itself, which means that they can be attacked in different ways. So there are a lot of reasons for why we would like to try to make the web more secure. If you look at our CIN model and what type of threat we can have, you see we have integrity, confidentiality, and, well, here they call it denial of service, but that is against availability then. And then they also have an extra row here for authentication. I said we can add additional goals, not only the main goals. So you see, for each of these, there are different types of possible threats that we need to think about. For integrity, for instance, modification of information is the obvious one. That can be done in different ways. It can be information while in transit, it can be on the web server, it can be in memory or stored, the files system and so on. And the consequences are, well, depends on what information you lose or are changed. Typical countermeasures, as we've seen before when we talk about encryption algorithms, are checksums, cryptographic checksums, where we can see that if anything has happened. But of course, we would also like to stop the change, and then typically we need to have access control of different sort in order to stop it. For confidentiality, well, then someone is listening in on different places again to gain information. And again, there are many different attack vectors for that. And here we have encryption as the main tool. But again, access control can also help, depending on at what stage they are. We lose the information where the attack is. For denial of service, well, there are different types of denial of service attack, targeting the network, targeting the machine itself, targeting the client, or where we are. All of them means that we are missing, we are failing to use the server, we can lose information even. That, as I said before, is very difficult to prevent. We can easily see this is an active attack. We can easily see it happened, but it's hard to protect against it. There are some ways we need to really build up a larger networks where we can take that attack and swallow it and still give access to the user. And that is typically not something a normal organization can handle. So that is typically we have to rely on our network provider, that they can offer such a service, that they can handle and stop the denial of service attack. And authentication, of course, impersonation and so on. We need, of course, authentication methods to stop it, but we can also use cryptographic techniques. So even if someone is getting access, they couldn't access the information, hopefully. So, where are we when we talk about web? Well, if you talk about web, we are really here, right on the application layer with HTTP protocol. That's the main protocol for web then. If you now think about why we should try to put the security for the web, we have options. We can put the security at the application level, or we can try to push it down to the transport level or down to the network level. So what would the effect be of having the security at different levels here? If we put it at the network level, what would that mean? Well, that would mean that the connection between one IP port and another IP port would be protected, because that is what we have at network level, port-to-port communication, or really IP-to-IP communication. Sorry, IP-to-IP. So one computer to another. I mean, we could go down even further. We go down to the link layer or physical layer, and then it would only be one physical link at a time that we would protect. And that would obviously not be very appropriate if you talk about web security. Of course, just encrypting one link somewhere wouldn't help to protect the web against attacks from the internet. But network then, because a web server would have an IP number. So we could put the protection at the IP level. But if you do that, then we would need to be able to establish connection between all the different other hosts that are connecting to our web server and our machine at the IP level and encrypt it. And since every type of traffic would go through the same IP number, it would affect all the traffic on that machine, not only web traffic, but whatever other service we're running would also be affected because they are using the same IP address. So going at the IP level might be too much because it will try to handle everything that's going on that machine. Now we're trying to emphasize on protecting the web server and the web service. So, but sometimes we want to protect everything, and we'll come back to that. And then, for instance, we have this IPsec protocol. But for the web, it's not really the best match. So then we have a transport level. Move up one step. And for the transport level, we have then port-to-port communication. And the web client opens one port, the web server has a port, and they start communicating on between these two ports. So that would be a one-to-one communication between two processes. And if another client opens up a connection, it will be another pair. But all of them will connect to the same port initially on the web server. And then the web server will probably spawn up new processes to handle each client. So we have parallel processes going on there. But it will be port to port. And if we do that, we won't affect any other applications. Because we can see that now someone is connecting to a web server, okay, fine, then we need to protect that. If someone is connecting to the mail on the same machine, we can see it's another port. We might want to protect that as well, but we can handle that separately. We don't have to handle it in the same way. So it will be more flexible, it will be more precise. We can tailor-made it perfectly for the web. So that might be an option. Application level. Well, yes, we could put it at the application level as well. The application could handle its own security at the application level, which means that we open up a transport connection without an encryption, but before we actually push something into it, we encrypt it, we handle security in the application, and then whatever we push down to the transport level is already secured. Yep.
How does it work when HTTPS and TLS, they're all on the same port?
Yeah, we'll come back to that. So we'll see how HTTPS and SSL and TLS, how they work together. So, yeah. It would be possible to put the security here. And for some protocols, we have chosen to put the security at the application level. For instance, Kerberos and S-MIME that we'll talk about later on. These are protocols at the application level, and here we have the security at the application level. But for web, we have decided not to put the security at the application level, but rely on the transport level instead. And it has another benefit, because that means that that type of protection that we have now developed for web on the transport level can also be used by other applications. Since it's in a service that is on the transport level, anyone that is using a transport level can use the same type of security service. So it's flexible, but it can be used by many different type of applications. So what we'll concentrate today on are these here then, SSL, TLS, and then later on SSH, which is also on the transport level. So these SSL, TLS then. SSL was the first version of these. Secure socket layer, created by Netscape, so it was not a standard, it was a protocol they developed because they saw the need of protecting the web. They were the first big web company to create web servers and browsers and so on. But once other companies joined and started working with web, they saw that there is a need here for a standard instead, not just a protocol that is owned by Netscape. So then the Internet Engineering Task Force created a working group to create a standard for it. And they came up with TLS then, Transport Level Security, which is really just continued work from SSL. So they are very similar, but of course improved over time. So the first version of TLS 1.0 is just a continuation. So we have SSL 1, 2, 3, and then TLS 1.0 is what we can consider to be 3.1 of SSL then. So it just continues on that stream. So after that, SSL hasn't been developed any further, so now all the work is on TLS instead. So this is the protocol stack when we use SSL TLS. It builds on the network layer with IP. On the transport level we have TCP. But now we add actually 2 more sublayers. So all of these 3 are part of a transport level in the TCP IP stack. They have put HTTP here, but HTTP should really be above because that is on the application level. But it connects directly to the record protocol. That's why they have put it like this. The rest of the protocols here are part of the transport level directly. From SSL TLS itself, we have the record protocol, the handshake protocol, the chain cipher specification, and the alert protocol. So these 4 are part of SSL TLS. And then we have HTTP, and that's here because SSL was developed for HTTP. But HTTP already existed, so SSL is not part of HTTP, so they are 2 separate things, but they are made for each other. And then at the end here we have something called the heartbeat protocol that was added later on as an extension protocol to SSL TLS. So we'll talk about all of these. So we have the architecture of SSL is like this. We set up a connection, or actually we start here. We set up a session between a client and a server. So now we would like to communicate and would like to secure the traffic between our 2 machines at the transport level. We create a session. So that's an association between a client and server. It's created by this handshake protocol. So we use the handshake protocol to negotiate a session. While we do that, we define a number of SSL cryptographic parameters that is needed. Those are different keys that are needed, different initialization vectors. We decide exactly what encryption algorithms to use because we have a set of possible algorithms we can choose from. So once we have done that, we have now what's called a session then, where we have negotiated a number of things. Once we have that session, we can create connections. That is part of a session then. So one connection then is a transit. It lives just for a short while a session can last for days. But connection is short-lived. It can be just for one packet, or it can be for an entire session, so it can be longer as well. But it's for a specific purpose. We want to do something. Maybe we would like to download a file from web server. Then we might create a connection for that. And we still have to negotiate things when we have set up a connection. But we don't have to negotiate all the things, because a lot of things is already set up for us. So we build on what we already decided here, and then we just create a connection based on that. And that's why we have split it into parts. This one we only have to do once. And once we've done that, it's easier to create the connections. A session state, as see, is defined by a number of parameters with something called a session identifier, just an arbitrary byte sequence. We have a peer certificate. So certificates is an important part of SSL TLS. We know what compression method we're using, because we compress packets before we encrypt them. We have the cipher specification, what type of ciphers we want to use. We create something called a master secret, and that is used to create then all the different keys that is needed for each connection. And we have a flag saying it's resumed. That means that we can create connections from in this session. So all of this is negotiated when we create the session then. For connection, we also have quite a lot of things. Yeah.
If you're getting, let's say you have already established a session,
Yeah.
and now you're going to fetch an image from another site. Do you have to create another session for that new site, or will it just create a new connection based on the current session?
Yeah. When typically you only create a session once between a web client and a web server, and then for anything, if you want to fetch something, you just make a connection.
But what if the image is in another server?
Yes, if an image is on another server, if you have a redirection, then it depends. If that server, if that should also be protected, then yes, you need a new session with that other server as well. So it depends on if it's secured or not. Connections, as I said, these also require quite a lot of information. So for each connection we make, we need to, again, have what we call a server client random. These are more or less like identifiers, random numbers that we have. And then we have all of these, what we called, well, they are sort of keys. Server write max secret, client write max secret. So this is when we are creating our message authentication codes. We need a secret value to make it into a message authentication code instead of just a hash, right? And then for the encryption, again, we need client and server key. So we encrypt in different ways in different directions. So the client needs 2 keys and the server needs 2 keys to be able to communicate in both directions. And then we need possibly some initialization vectors, again depending on exactly what type of encryption and message authentication code we're using here. We might use that, or we might need that. And then we have sequence numbers, so we know where the packets come from in the sequence, because we typically send a number of packets within a connection, so we can merge them correctly. We'll come back to how we create these different numbers here. But let's look at different sub-protocols now then. So SSL record protocol services gives us different services. We get confidentiality and we get message integrity. Confidentiality, of course, by encrypting. And there are a number of different encryption methods we can use, as you see. This is now for SSL. We'll talk about later on changes with TLS And with TLS there are some changes in that, what is available. Also it said that we have compression, partly because encrypting and adding message authentication increases the size of packets. So compression will reduce that problem. We compress it before we apply the rest. So we won't increase the size too much of things we send. But also because encryption will actually be stronger if we first compress the information before we encrypt it. We'll talk about that more when we are talking about email security. And then we have integrity to add a message authentication code. So all of that is done for each packet that is sent.
Excuse me?
Yeah.
They stop work on it and they don't improve it, they work on it. But why do now we say SSL certificate, SSL protocol? I'm really confused. We use SSL or we stop using it? I don't understand.
We use what? Or stop using what?
SSL or we still use it or not? Because you said tell us they work on instead of SSL.
Yeah.
So why we
Do you mean why we use these encryption with if we have certificates or?
no the SSL itself.
Yeah, SSL and TLS both are very similar. Both of them are negotiating a session between client and server. During that session you have to authenticate yourself. You do that using a certificate. And then whenever you would like to send some data, you have to encrypt it.
Yeah.
And when you do that, you use these encryption algorithms.
The previous one you said SSL stop work on it and they work on TLS like a standard.
Yeah, SSL is not used anymore typically. So TLS is used instead today. But it's just that it's an older version of SSL or TLS you can say. SSL was the starting point and they developed a number of versions of that. And then that was put on the shelf and the work was still continue on TLS instead.
Okay.
So today it's TLS that you should use.
Yeah, but why we say SSL?
Because everything comes from SSL.
Okay.
And TLS is so similar. So what we discuss now first is SSL, and then later on we just talk about the difference in the new protocol. So this is what happens whenever we would like to send something. Here you have some application data. This application data could be a web page that you fetch, or just an image that is part of a web page, or a form that you would like to push. You would like to send you fill in some data on the form and send it. So the application data is anything that goes back and forth between the client and server. It could be just a byte of information, or it could be 10 gigabytes of information, depending on what you access, what you're doing. The first thing that happens is that it's fragmented if needed. So we have a certain maximum size. So we split them up in small parts. And then each fragment is compressed, typically using the same compression as you have in zip. After that, we calculate a hash over this compressed and calculates a message authentication code using the server or client max secret that we have negotiated, depending on if we are on the server or client side. Then we encrypt everything, both the compressed message and the MAC. And after that, we append an SSL record header to it. And the record header is from one of the protocols in the SSL family. And then we send it. And then, of course, we do the same with our fragments. And when we arrive at the other side, we de-encrypt, we check the MAC, we decompress, and then we merge the fragments together and push it up to the client or server. So this is the SSL record format. So this is the header that we have here. And the content here is what we have in the rest of this. So the content is just the compressed, encrypted message with the MAC code at the end here, which is also encrypted, right? So that's what we've done on the previous page. The header contains this information. So it's very little actually in the header. Talk about the content type. So there are a few different possible content types, depending on if we are negotiating or if we are now sending data, whatever. We'll come back to that. We have a major and minor version here, and that is if it's SSL 2.0, 2.1 or whatever. So it's a version of SSL or TLS. And then a compressed length here, which tells us how much data we have inside here. And since this is a fixed size field here, there is a limit for how big one packet can be here. And that's why we need to fragment the application data, or might need to fragment it. So that's the SSL record protocol. Record protocol typically is doing this transformation and put the header on it. And that's what record protocol is doing. Then we have the change cipher specification protocol. Let's go back here again to this slide here. This was record protocol. Everything goes through the record protocols. Whatever we're doing, we will compress it, encrypt it, and put the header on it. But above the record protocol, we have all the other protocols. So the change cipher specification protocol is one of those, who is above the record protocol. So that's what we're talking about now then. The change cipher specification protocol is the simplest protocol I have ever seen. And it's quite strange actually that it is separated as its own protocol. Because the protocol consists of one single message, and that single message is the 1 byte containing just one. Yeah?
Every time.
Every time. So whenever you use this protocol, you send 1 byte with the content 1. What that means is that we now change phase. We go from unencrypted to encrypted connection. And by being able to decrypt this message, we confirm that yes, we have been able to negotiate correctly, because now we can decrypt it and see that we actually get that information. So that's why it's so simple. We only need to be able to make sure that we can decrypt it in a correct way. If we can do that, we have now an encrypted session. The alert protocol is also quite simple actually, but it's a little bit more complex. This is the content of alert protocol, 2 bytes with level and alert. So if we send an alert, let's go back again just to make it very clear. If we would like to send an alert, what you do then is that, we can go back all the way here. The alert protocol up here, notice something is wrong. That can be any time during the communication. It could be during the handshake when we try to negotiate a connection, or it could be later on that we suddenly realize something is wrong here. The certificate doesn't hold up any longer, or we have lost connection, or the server has a process that broke down so we couldn't service anymore, whatever. we would like to send an alert to the other side. So we create that alert, 2 bytes, and we push it down to record protocol. It's compressed, it's encrypted, we add it back, add the SSL header, and then it's sent over. So now we're here then. So this is the message part, 2 bytes. And it's level and alert. The level can be fatal or it can be a warning. If it's fatal, it's just we tell him the other side, okay, we have to stop. We can't continue now. And then we tell the reason for it. Decompression failure, handshake failure, illegal parameter, all of these are seemed so severe that we couldn't continue. But it could also be just a warning. And if we're just a warning, we could continue, depending on what the other side thinks about it. So that's the alert protocol. And then we have the handshake protocol. And that's a little bit more complex. So during the handshake, the server and client authenticate each other. We negotiate what algorithms to use for encryption and message authentication. We negotiate keys for all of that. And we do that in 4 phases. So in the first phase, let's see, we establish capabilities. In the second phase, server authenticate and we start the key exchange. In the third phase, the client authenticate and we finish the key exchange. And in the last phase, we finish up and start using whatever we have negotiated. This is the format of the handshake protocol. 1 byte first with the type of message that we have. And there are a number of different types of message we can send with a handshake protocol. We have a length, and then we have a content. And depending on what type it is, the content can be 0 or it can be a very long content. The content could, for instance, contain the certificates. So these are message types. That's a hello request. Hey, I would like to communicate with you. No parameters, same. It's just an initial thing that we start up with. We have a client hello. Suddenly we have quite a lot of parameters. We are telling the version we're using. We give a random that is used to create different shared values. A session ID, what ciphers we are supporting, what compression methods we are supporting. The server hello, again, similar things. We can have special certificate exchanges. And now we're using these X509 certificates we talked about. And there are, as you see, a number of other types that are used in different phases of this handshake. And this is the typical handshake that we have. So here we have the 4 phases that I talked about. First phase, client hello and server hello. Second phase, we said that in the second phase, server authenticate and we start the key exchange. Server authenticate by sending its certificate. And then we start the key exchange here. And then we request a certificate from the client. And then we say, now we are done with our phase. And then we have the third phase. And now it's the client's turn to authenticate. We do that by giving our certificate. We exchange the key values from our side. And we verify the certificate that we got from the server. Say, okay, that's fine. I can approve that one. You can see that some of these are shaded here a little bit. They're a little bit gray, and they are optional. So it depends on how we set up a handshake. What type of requirement we have. If we require a certificate or a client certificate or both. That can be optional. After the third phase, we're ready to go, but we haven't started doing anything yet. We have just negotiated. So now, as part of fourth phase, we kick in the cipher specification change protocol. So here we'll get to send this 1 byte using the other protocol. So this is quite strange. Why didn't just make this phase part of the handshake protocol? But yeah, that's what it is. So we send 1 byte here, encrypted now, with what we have negotiated. And then we say finish. And on that side now, if we can interpret this correctly, we can understand whatever we get from the client here. So then we are sending back this 1 byte encrypted from us and say, okay, we are also finished. And if a client can understand this now, he knows that the server is okay, and we understand, so now we can actually start sending data. So this is the basis for the handshake protocol. Of course, things can happen here. We can have alerts saying, well, I couldn't recognize your certificate. Try resend another certificate, or it can be that we don't support that encryption method you want to use, so you have to use something else. So it can be more complex. So this is the normal simple flow. The cryptographic computations are based on something called a master secret that is created during the handshake. And the master secret is, let's see, a one-time 48-byte value generated using either RSA or Diffie-Hellman. And that is done here then through a key exchange here. We know that Diffie-Hellman works that we just send one message in both directions. So after that, both can create this shared secret on both sides. We can do the same thing with RSA. So after this exchange, we have a shared secret, which is this master secret. From that now we generate all the other cryptographic parameters that we need. And we need, as I said before, these MAC secrets for a client server. We need the keys that we'll use to encrypt the traffic. And whatever initialization vectors that we need depending on what method we're using. All of these are created based on this master secret in this way. So we're using HMAC, as you see. We start with a seed that is also negotiated. Then we put in the secret into the HMAC, and we get the first output from HMAC, which is dependent on whatever hash algorithm we're using, right? So if we use HMAC together with SHA-1, we get 160 bits output. If you use it with SHA-512, we get 512 bits output. So it depends on what we're using. But that may not be enough to create all of these secrets. So if we need more, we just add one more step here. We take the output of this, put it into a seed, and hash the secret again here. That will create a new value down here. And if we need more, we just continue. We do this as many times as needed to create as much data, so we can create all of these keys and initialization vectors. And this can be done on both sides, because both have this master shared secret that we negotiated. So now after this, both sides have all the keys that is needed. Which means that now we can use symmetric encryption all the way from here, which we know is much more efficient. Yeah?
Maybe I didn't hear it, but why do you hash the secret again? Why do you do that?
You mean continue in the flow here, or?
At all. Why do you run it through the p hash? The secret and the seed?
Well, we do that because we need to create all of these different values here. And just the secret enough, most secret is not long enough. So we need to be able to create more bits. And that's why we hash it in this way until we have enough bits. So that's the SSL. If we now talk about TLS then, it has the same record format. It has the same sub-protocols. So it's very similar. There are some changes then. TLS version 1.3 is the current version that we have from August 2018, so it's about a year old now. And of course we had 1.0, 1.1, 1.2, so there have been changes in several steps. But what has been changed is the message authentication code. Initially they didn't use HMAC. SSL used its own message authentication code that was very similar to HMAC, but it wasn't HMAC. So that's a small change. How to expand the shared secret is also a little bit different. More alert codes for the alert protocol. Cipher suits have been changed. We have removed some that are not considered to be secure anymore. Client certificate types. We can support different types now. How to do things a little bit has also been changed. But the structure of everything is exactly the same. But of course, if you implement it, you have to know about all of these details. And most of these small changes are made in order to make it more secure, to deal with different flaws that I found during the time. HTTPS then is HTTP over SSL. So when we say HTTPS, it's really just HTTP plus SSL TLS. And so HTTPS itself is not really a protocol because it's still just HTTP plus using SSL or TLS. But when we use HTTPS, we use another port. We use port 443 instead of 80, which is the default port. But as you know, we can configure, we can use any ports we like, but these are the default ports. If we use HTTP over SSL, what are encrypted? Well, the URL are encrypted. So whenever we request a URL from a web server, that is encrypted. Documents, form data, if we push cookies, and the headers. In principle, everything is encrypted in the traffic between the web client and the web server. It's only during the negotiation phase that we have unencrypted. But once we start to encrypt, everything is encrypted. If we look at adoption of HTTPS, these figures came from yesterday. So we can see that the old protocols, SSL 2.0 and 3.0, are supported by some websites, but not very many. Less than 7% still supports then SSL. And it's going down even further if you go back a little bit. TLS 1.0, 1.1 is supported quite a lot, but it's going down. And the reason is that there are some security concerns depend on how you implement the protocol. So you can implement in a way, depending on what features you use in it, that makes it insecure. 1.2 is also having some problems actually, but it's supported by almost all web servers today. And 1.3 that has been around for a year now is still only supported by less than 20% of web servers in general. There are no vulnerabilities so far known in 1.3. I'm sure some will pop up eventually. So that's the situation on the server side. What about the client side? Well, on the client side, you use a web browser, and you don't really have control over what they support. You can choose web browser, but that's what you can do. If you look at web browsers now, everyone supports 1.2, and most also support 1.3. If you went back a year, 1.3 was only supported as in beta versions or test versions, but today it's supported by all except Microsoft's Internet Explorer and Edge. For some reason, they had test supported a year ago, but in current version it's not supported. I have no idea why, actually. So if you set up a web server, try to make it talk TLS 1.3. But as you see, not everyone can do that on the client side. So to be able to support all clients, you need to sometimes back down to 1.2. And if you do that, make sure that you don't do any of these errors in the implementation, because then it is actually secure.
But will they flag SSL 3.0 as insecure right now?
3.0, yeah, that is insecure today. There's no way to make an SSL 3.0 installation secure, because there are in the protocol itself there is enough insecurities. The heartbeat protocol was also one of his helping protocols, extra protocols, and that was added later on as an extension to SSL TLS, and typically used if you have a web server. So a heartbeat is a periodic signal generated by either hardware or software, just to tell the other side, I'm still active. Because if you think about how web connection works, you go to a web server, you fetch a web page, and then you might sit there and read that web page for a long time before you do the next thing. So even if you think you're still active, it's not seen on the network. And what could happen if you don't active? Well, web firewalls, NAT routers on, typically drop a connection if I don't see an activity for a certain time. So that's really the reason for why the heartbeat protocol. To just make sure that, yes, I'm just sending, hello, I'm still here. So the network can go through the network and everyone sees, yes, people are still using this session here. So that's the main thing for the heartbeat. And it's a quite simple protocol. See, heartbeat request, heartbeat response. You just say, I'm here, and the other side responds, okay, I hear that you're here. Okay, let's take a break before we go in and look a little bit on the attacks. So, 7 minutes break.
I'm really confused
Yeah.
about SSL and TLS. HTTPS is like HTTP with SSL, yes?
It's in principle the same protocol. It's just that
Yeah,
TLS is newer than SSL.
yeah, but HTTPS is HTTP plus SSL, yes? Or not?
SSL or TLS.
Wait,
Uh-huh.
you install it and then export it with the
Hola.
Okay, so it's not because there is like SSL certificate. They don't say TLS at all. Why? I don't know. It's like the name. They prefer to say SSL or.
Well,
'cause it's
SSL is so.
It's confusing. For
Yeah,
you
but
understand?
when I say SSL, it can be SSL or TLS
Okay.
because I mean, it's so common that we're talking about SSL for so long time. So even if SSL is not used now, it's TLS. You still think about it as SSL. Actually,
Okay.
yeah.
Yeah, because
Install it, right?
yeah, it's confusing. Like for me, it's
Yeah.
because they say stop using and they say okay.
Yeah, but it's still called the SSL record protocol, for instance, even if it's TLS. The sub-protocol is still called SSL record protocol, so you still have the old terminology in the new version of protocol.
Okay.
Yeah.
Yeah.
Like you said, like 3 slides or 4 slides back when the protocol, the initiation protocol between this
The handshake.
the
Yeah.
handshake. That is not encrypted.
No, not until
Can it
you.
not be that session be hijacked?
Oops.
Yeah.
Here.
Yeah. Can the session not be hijacked?
All of this is in clear text until you send this message. This is encrypted. So this phase is encrypted, but not up here.
It's vulnerable then.
What you can see is, okay, you can see who is communicating. You can see what type of encryption algorithms they're using. That shouldn't need to be secure, since we said that the security in encryption is based on the key, not that you hide the algorithm. So it's okay to tell you what algorithm you're using. You send the certificates. Certificates is something that you publish online. That doesn't have to be encrypted. Then you have these key exchanges. And what we said when we talked about Diffie-Hellman is that whatever you send in a key exchange can also be known by anyone. It doesn't matter, because it's only these two parties who can create this master secret from this information. It doesn't help that you can see that. You can still not break into it. You need to know one of the secret values on each side.
So you
So
have
it
the
doesn't
private-
matter that all of this is known.
Okay, but if you have the private key, then crack everything.
Nope.
You know, I have a question about. You know, we said another 3-way handshake.
Yeah.
This is after the 3-way handshake or before, or which layer it is?
Uh,
Because, no, we study in the network, but every course give me like a piece of the picture. I don't have the whole picture.
That's because the whole picture is too complex. You have to talk about small pieces at a time.
Yeah.
If you try to talk about everything, you would die. But if we go there, if we go to, oh, sorry, wrong way. If we go to
No, but I'm not gonna run them. I mean, I know that they work. That's not the issue. You have to show.
this picture,
And another picture.
I mean, the three-way handshake is here, right, on the TCP
Yes.
protocol. Exactly. So what happens is that if you use SSLT or TLS, before they can send their first packet, they need to set up a TCP session. And when they set up a TCP session, you have this free handshake,
Yes.
three-way handshake. Once that is done, then you can start sending these messages.
But I'll ask
I
Andy tomorrow.
need also
I know
handshake.
because I know that you're.
Oh yes, you have to handshake on this level.
Yeah.
And once you've done that, then you can start sending these packets.
Yeah.
So this four-phase handshake protocol is coming after you made the three-way handshake down here.
Because then it's all black and white, and then only gold is like.
You need to have the TCP session open so you can actually send data before you can start on this level. And that's typically how it works all the way. Each level has to fix its own problem. So on the IP level you have to find the other side. Here you have to negotiate. Here you have to make that. And here you contact between the client and server. So it's a general picture of how it works.
For some
Yeah.
funky reason.
It's better now.
Yeah, good.
Thank you. Thank you.
That was early 2000s.
There was Alicante and like almost in Italian. And there was a video of it like pulling it. Like a mini tornado, like we never have it either. We never get tornadoes in Spain. It's probably like the first time.
About this island?
You want to split that sum file into two. You don't have to. If you want to get a key, it should be both. When you convert it to PM,
No, this is better.
Tastes like handsome. Smells like the gummy handsome. I'm gonna drink water before the break.
There's coke stuff.
Wait, when does it break it? Fuck, I need water.
Okay, so let's continue with some attacks against SSL-TLS. There are different types of attacks that you could try to perform. You could try to attack on the handshake protocol. If that would work, you would be able to capture the keys that are used, and then of course you can follow the entire conversation and decrypt everything same as the client and server would do. So that would of course be very bad. You can attack the record and application data protocols. Trying to see if you can make it not to encrypt some part of the traffic, or if you can extract that information, even if it's encrypted, and use some information. That is more tricky, because then you would have to have more control, more understanding of what's going on. You can do attacks on the PKI. What does that stand for? Yeah, public key infrastructure. And that attack would then be typically to try to forge certificates, for instance. If you do that, you can pretend that you are someone else, set up a fake web server, and that way you can capture information and so on. So that would be an attack, and that is, as I said before, we talked about certificates, that has happened actually. And then there could be other attacks that are more technical, or there could be social engineering attacks and so on. So there are quite a lot of different types of attacks. One attack was called the heartbleed attack, and it was a lot was written about it some years ago now. A security bug in the cryptographic library. So it wasn't actually a flaw in the protocol. It was a flaw in an implementation of the protocol. But it was one in the OpenSSL, which is one of the most common libraries used to implement SSL. So it was a lot of web servers that were affected by this bug. And it was using the heartbeat protocol, that's why it's called heartbleed, to attack the servers. And what it did was it sent a lot of heartbeat packets in a certain pattern, and in that way it could create an buffer overflow attack, and then it could extract data from web server by just repeatedly sending heartbeats in a certain way. And it could extract important data, so you could take over a web server from after this attack. And since it was quite easy to perform and lots of servers were affected by it, it was a famous one. One way to try to handle these types of attacks is with this additionally protocol, which is called as the HTTP Strict Transport Security Protocol. The idea with this protocol is to stop certain type of attacks which are called downgrade attacks. If we look at this table here, we see that it's only 1.3 that is really secure. If you can force the connection between the client and server to downgrade and use lower versions here, older versions, more attacks will be available for you. So that's the idea with a downgrade attack, to make the communication with a lower version of SSL TLS. The idea to set up that is, well, you can do it in different ways, but one possible way is that you set up a fake web server. And then someone connects to that thinking it is another web server. And then you downgrade, and then you can extract information by downgrading the connection between you and that fake web server. Or you can just manipulate the connection between a server and the client and make the client downgrade the level of SSL TLS by dropping certain packets or changing certain packets. It will downgrade. And then if it downgrade enough, you can again capture information and possibly break that connection. So that's why what the purpose of this one is to stop this downgrading, because it's part of the protocol. And the idea with downgrading in general is that, well, depending on who you are on the other side, you may not support what I support, so we need to be able to downgrade until both reach a level where we can negotiate. If you have a very old client, it should still be able to connect. That's the idea with this negotiation where you can downgrade. But since we now know that we have these problems, we shouldn't allow that. Protocol works like that you set up a policy for a web server, and whenever a client connects to you the first time, HTTP or HSTS will send you a policy saying that for my web server, you should never downgrade below, say, 1.2, TLS 1.2. I will not accept that. That should now be stored by the client. And whenever the client later on tries to connect to this web server, it looks in the policy, okay, I should never use that. And then if someone tries to force you to downgrade, you have a policy, no, I shouldn't do that, so I will not do that. So you will not be tricked into downgrading. So it's a quite simple idea, but it can help. Of course, it means that you first have to have one connection with a correct web server to get that policy. Okay, let's move on to Secure Shell, the second protocol on the transport level. We're going to talk about the main protocol. Designed 95, so it's quite old now. It was developed early on and standardized. So it is a standard now, and it's working on the transport level. If we compare SSL and SSH, SSL or SSL/TLS then outnumbers, today it's TLS then, outnumbers SSH a lot. If we look at how much communication on internet is secured with either one, I would say that TLS is probably 95, 99% something of it, and SSH is the rest. But it does have some specific functions that for some applications it's absolutely the best. Some features. First, it has a very flexible authentication. You can decide what type of authentication you would like to have. We'll come back to that. It has something called perfect forward secrecy. That is not unique to SSH. There are a number of other protocols that have the same feature, but at this time when it was created, it was quite original. It's the last point here that is the most important in that. You have a permanent key and you have session keys. So whenever you communicate, you first have a permanent key and then you have session keys. So different parts of a communication will have using different session keys. Normally, you create this session key based on that permanent key. And if you don't have this perfect forward secrecy, if you for some reason would be able to capture that permanent key, you will be able to decrypt all the communication regardless of which session key was used. So you can go back in history and so you just collect everything, you come back. But with perfect forward secrecy, it's only the current session key that is working. Even if you capture the permanent key, you couldn't go back to communication that was encrypted with earlier session keys because you couldn't still decrypt those. So it requires, of course, a certain implementation, but it's a nice feature because it can protect all old traffic. Then it has this unique port forwarding that is the main reason for why SSH is used today. Except, of course, as just a terminal program, which is also that you can use an encrypted terminal. But except for that, it's for the port forwarding. So port forwarding provides security to any TCP/IP application, any TCP stream or session you can protect with SSH. And that's why we say it's protection on the transport level. And the nice thing with it is that the application that is protected doesn't even have to know about it. You can have old application that doesn't know anything about security at all, and you can secure them with SSH. You don't have to rewrite the application, you just have to configure your computer to use SSH in the correct way to secure any traffic. If you compare that with Kerberos that we talked about before, we said that to use Kerberos, you need to have Kerberized applications. So the application need to know about Kerberos in order to work for Kerberos. For SSH, that is not the case. So this is in general how the port forwarding will look more closely at it. You have a number of applications that is running in a client. Whenever that application would like to connect to a server, normally in that application you point to the IP address and the port number at the application, right? You'd say, the email would like to talk to the mail server here on this IP number and a certain port number. What you do now is you configure your email to say that, well, instead of communicating this one, we actually send it to ourselves. We are sending it to the SSH client on a certain port number. And then in the SSH client, we have configured that anytime traffic arrives from this email application, we will forward it to this port over here. So initially, it just works as a proxy. You send it to the SSH client and it passes it on. So far, it could have worked exactly the same as before, just that we proxy it. But now we also add that the SSH client will also encrypt the traffic and send it through this secure tunnel. And all the traffic that is sent will go through the same tunnel. So from the outside, we only see that there is one connection between the client and this firewall or this, well, where the SSH server is. And we couldn't see what type of traffic goes in the tunnel. If it's email traffic, database, or if it's normal terminal, whatever. Everything will be in the same tunnel, ending in the SSH server, which then forward it to the correct port number internally here. So here we see the details. A TCP client is configured to send to local host on a certain port. And it is the client, SSH2 client, who listens to that port and then encrypts and forwards the traffic to the server on the side, who decrypts it and then forwards it to the TCP server that is the target for that traffic then. Does that make sense, or any questions about how that works? As you see, you don't need to change the client, you only need to configure an IP number and a port. And that is something that you do in clients normally. Of course, there could be clients that have hard-coded port number, an email client who would only talk to a server on port 23 or whatever. And if that is the case, then it wouldn't work, because you need to be able to configure what ports to talk to here. But most general TCP clients, it's possible to configure both IP address and port. As part of SSH, you also have some additional things. You have an entire secure file transfer protocol that is part of SSH. So as long as you have set up this tunnel between the client server, you can also start sending files in a secure way, which is nice. This part encrypts username, passwords, and of course all the data, the files that are sent. A nice thing with the tunnel in general is that it doesn't cause you any problems with firewalls or NAT routers. Especially here, what is the option? Well, the typical option here would be the normal file transfer protocol, FTP, which is using two different ports, one for commands and one for data, if you run it in active mode. And that can be tricky for a NAT router, because one connection is from inside and one is from outside. But with secure FTP, you just send it through the same port as SSH already have. You only use this port 22, and it doesn't see any different. No problem with these ports. Let's see, I have a question here on the Slack. Isn't SSH often built using SSL? For example, OpenSSH generally built with OpenSSL linked. How is this connected? I have to look into that, but I don't think so, because if you look at the protocol, they are separate, completely different protocols. Of course, there could be an implementation of one that is using the other, but then it wouldn't be a standard implementation. So I will, okay, we got a reply as well on it. Let's see what someone wrote about that. Okay, a link here. Okay, follow that link, but and I will do it as well, and we can talk about it next time. But I would be surprised if that was a general case at least. So that's SFTP. One use of this is to fortify a server that is outside a firewall. If we think about a typical situation, we have a firewall that protects all our systems on the inside. And then in that firewall, we can filter out a lot of different traffics. If we put a server on the demilitarized zone, that is typically outside a firewall, we could have another firewall outside this one to protect. But if we don't do that, then of course this server is a bit vulnerable because all the attacks from outside directly hits it, which means that if you want to fortify that one, you should close down as many ports as possible so it's not open for attacks. And a nice way would be to just have port 22 open then, and of course 80 if it should be a web server as well, but very few ports open. And then you can have a secure connection either from clients working on outside or clients working from inside who need to manage it. All of them can access it in a secure way using SSH and possibly STPF or SFTP. Okay, that's an interesting discussion here on the Slack, but we'll come back to that. Okay, so the components of a secure shell is then the server side, which you call SSHD, daemon, that runs on the server side. And then we have clients that you need to install on any client that would like to connect. We have sessions that we are creating between the client and server. If you look at the architecture, it's similar to SSL TLS, but it's not built exactly the same. We have the same components, of course. We need to handshake. We need to be able to exchange information to create keys and so on. We are setting up sessions and so on. But some differences. SSH initially didn't support certificates. It did support public keys. We could use public keys in order to authenticate, but not supported by a certificate. That has changed now, so now it does support certificates as well. And you can remember, you can associate another host with a key, which we'll come back to when we talk about authentication. Yeah, we'll come back to that tax as well. So, as I said, all the connections are done on port 22. Whenever we have a connection, the daemon on the server side is listening on port 22. Whenever we find a new client, we spawn a new process to handle that. So each client is handled by a separate process in the same way as we've done on the web server to spawn processes to handle each web client. And for each child, we negotiate, again, new parameters, of course. So each client has separate parameters. Otherwise, it wouldn't work for us. So these are the protocols. And as see, it's still built on IP and TCP. And we, again, have two different levels of protocols. But now we have just 3 protocols instead of 4. And actually, what the different protocols are doing is not exactly split in the same way. So, if we start with a transport layer protocol that we have down here, it handles confidentiality and integrity. That is the same as SSL TLS. We're doing encryption, we are calculating MAC codes. but it is also handling the server authentication part. So the server authenticates at this level, while the user authenticates using the user authentication protocol. So they split up the authentication in two different protocols, depending on which side authenticates. And then we have a session connection protocol, which handles all the different sessions we have. And different sessions are, well, first we have different sessions for all the different client machines, but then we can have different type of connections as well for different machines. So we can have these secure file transfers, and we can also have something called forwarded X11 connections. That is also another thing that is supported by SSH. What is X11? Yeah.
The display manager for Unix-based.
Yeah, it's a display, remote display, graphic remote display for Unix machines. As you say, it's an old standard, but it's still working, where you can ask the other side to, instead of launching a process and the user interface on one side, it can launch it remotely on another machine. And if you use SSH, you just forward these X11 sessions through the tunnel, so you get that in a secure way then. So it's a nice feature as well. Whenever you run in the CS cloud, I'm not sure if you use that feature, but you could use X11 to have a graphical interface towards the Linux machines in the cloud. So we have these three protocols, and as you see, the division of work is a little bit different than SSL TLS. So on a transport layer client initiate connection, we identify, we again tell what type of algorithms we want to use, we do a key exchange, and again we use Diffie-Hellman typically here to do a key exchange. The packets are formed also in a similar way. The payload is compressed, we encrypt, and we add a MAC code. So again, as you see, it's very similar to the packet format of SSL TLS. There are details that are changing. Here we add a sequence number. We have some, as you see, packet length and padding length here, and we have padding at the end. So they built it a little bit differently in the headers, but we're doing the same type of operations. If we look at cryptographic algorithms, there are a selection of algorithms supported. See, they recommend that you use AES with at least 128-bit key for encryption. For the message authentication code, they actually recommend SHA-1, which is a little bit strange. But well, I think that has been changed now actually, because they support other algorithms as well. And compression is not required, but if you do use zlib, which is in principle the same as SSL TLS again. Authentication can be handled in different ways, as I said before. It's a very flexible framework. You can authenticate with a number of different ideas. Let's see, I think we can skip that. So the first one is the public key method. So a possession of a certain private key is the proof that you are who you are. If you can encrypt something with your private key and the server on the other side have a public key, then that is authentication enough. Without a certificate now then. So the user sends a request for use of a public key, and then we just check that we can decrypt what is coming. We have a password method. So then we are sending a message saying that, okay, would you like to authenticate using a password? And then we just send a name, and then we send a password. And that is sent by the client authentication protocol, because it's the client who authenticates here using the password. And the client protocol is not encrypted, but it has to pass through the record protocol where things are encrypted. So on the network it will be encrypted. We have something called host-based authentication. And this is a case where you actually authenticate not a certain client on the host, but the host itself. So if you are on one Linux machine that has been working towards another machine using SSH, now the machines are authenticating against each other. And if another user on that machine now connects to that machine, it's the machine who authenticates. So you don't have to authenticate each client. Of course, this is something that you may not want. You may want each client to authenticate, but it's up to you when you set up if you support this or not, of course. Well, I think we'll mention a connection protocol, that it handles different type of connections, each for different clients, X11, file transfer and so on. And all of these are multiplexed into one tunnel on port 22. Attacks against SSH. Well, we have something called a man-in-the-middle attack. That is something that potentially is a possible attack for any protocol where you have two parties who need to negotiate things. And depend on what type of authentication here, it could be possible with a man-in-the-middle attack. And especially if you use this host-based, you have to, or with private keys. They could be attacks with man-in-the-middle. So that is a limitation with SSH, but you need to think about how you actually set it up with authentication in order to make it really secure. There's no really good solution for it as far as I know. So depending on if you set it up incorrectly, it can be attacked in that way. Of course, denial of service is also something that any protocol can be attacked by. Here you can do it in a way that is a little bit smarter, because you can always perform a denial of service by just sending so much traffic that the network connection is flooded. But what you can do here is that an attacker is connecting the SSH server to make it start setting up connections. And for each connection, it requires quite a lot of resources. So you just establish a lot of connections, and eventually the server is taken down by handling all of these parallel connections. It's a very similar attack as you can do on SSL, actually, TLS, setting up false connections, or even on TCP level by just setting up TCP connections. Yeah.
Can you configure how many active connections? Or like
Yeah,
active connections?
you can do that. So you can make sure that your server doesn't crash. But then the effect of that would, of course, be that you would stop some legitimate users who try to connect if you're under an attack. So, yeah. Okay, that means we have time for another Kahoot. Let's see.
I'm telling that to you that
So, full screen. Think I will lower the light. Should be better for those on distance. I know it's a little bit hard to see on distance, see the questions, but or actually the different options, but try. And today the Kahoot is again looking back a little bit on certificates and how we can use certificates. So I hope you have studied hard now. You know this will come now and then. Who's the favorite? Well. Still increasing. Let's see if someone else is joining. 28, yeah. 29. Okay, are we done? No one else waiting? Okay, I think it's more questions today, but we'll see. So let's start then. 12 questions today. Okay. One to go. Okay. Well, the majority is right, but there's still a few who need to think a bit. Digital certificate is used with asymmetric because we are protecting the private public key pair, or actually it's the public key that we create the certificate for. There's no certificate created for symmetric encryption keys. Nickname XDXD. Okay. So next one. So a digital certificate links a public key to the user or device. It links, I mean, that's what you have in certificate, right? You have a subject name, and that subject name is a device or a person. A private key should never be connected with it. I mean, it's connected mathematically, but it should not be known by anyone. So we don't want to involve that here. The plain text and ciphertext doesn't have really anything to do with a certificate, right? It will be used later on. New leader. Okay, next one. Good. Best result so far. A certificate of authority issues by sign it with its private key. Excellent. Nils still in the lead. Nickname is going down. Okay, next one. Okay, well, we talked about this just now, right? We shouldn't have a private key in the certificate. Expiration date, yes, we have both valid from to. So we have expiration date. Owner's identity, yes, that's what we link it to, the subject name. And the serial number, yes, there are serial numbers. Actually, there are in version 3 we have 2 different serial numbers even. Okay, but most got it right, so that's good. Nils still in the lead, but it's very close here. Very, very, very close. Okay, good. Next one. Okay, we actually didn't talk that much about the registration authority. We mentioned that the registration authority is part of this process in the PKA, but we didn't talk very much about it. But this is what they do, customer facing. They are, if you want to have a certificate from, say, VeriSign, as I said, we'll come back to this later when we talk about different levels of certificate. But if you want to have a type 3 certificate, that means that you in person have to show up and prove who you are. You don't want to go to the United States to do that. So instead we have these registration authorities where you can go and they check who you are, and then they tell VeriSign, yes, I have checked his identity and it's okay. So now you can issue a type 3 certificate of that person. Okay. So that was a bit tricky. New leader, even if Nils is on fire. Okay, next one. Okay, why is this true? Why didn't everyone think it's true? Either the owner or the issuing certificate authority can revoke a certificate.
If my private key is compromised, I can tell the CA to revoke my...
Well, as I said, what you need to do is, if you have a private key, you can revoke it. And the owner has the private key, so the owner can revoke it at any time. The CA doesn't need to know the private key to revoke it. It just have to add it to the revocation list to revoke it. Anyone else could revoke it, but only if they have access to the private key. And if that is the case, then we would like to have it revoked anyway. So it's not a problem. So if you have a private key or if you're the CA, you can revoke it. Okay. Back on top place. But I do think we have some new names here as well. Nice. Okay, next one. Good. What are the rest here? X25, what is that? You should know. We talked about it in the networking course. Yeah. Well, it's a protocol for data exchange, typically long-range serial connections. If you set up a wide-area network with, you can use the X25 network to set that up. X400, what is that? I don't think we talked about it, but you may know about it anyway. No? It's email. X500. Well, that's a protocol for directory information, how to store information. And X509 is just one example of that. That's how to store and handle certificates. So X500 is more general, how to handle different types of information in a structured way. But the main thing is that you know about this one, and you did, so that's fine. Okay. Nils is winning, it seems. Okay. Great. Public key infrastructure, almost everyone got that right. I don't think the other terms exist, just made up. Since the top 5 is fixed now, you have to try to break in now. Okay, next one. This one you should know. Oh dear. If you didn't get this right, you were probably asleep today during lecture. This is what we talk about today. TLS SSL is what we use with HTTPS. Fire again, streak of 9. Nice. Okay, next one. Well, everything is right, you could say. But the only thing that is really, really right is all of these. Because we have a key exchange. We do handle encryption, bulk encryption with symmetric encryption. We do message authentication. So we do all of them. If you got that wrong, you're probably too fast. Yeah, new leader. competition. Now, I like this. Okay. Okay, there are two more, I think. The next one. What is port 80? Yeah, the normal is 81. Me neither. 443 is 1480 PS, and 8080, what is that? Yeah, alternative port for HTTP. Okay, last chance now. It's your boy, DK, and who's that? Ah, right. You have something to prove now then, last one. Okay.
He won.
Not far off, bro.
Well, some needs to study a little bit more, but yes, SSH is the one. So, yay! Good work! Okay, so everyone, yeah, you got it all right. And second to just one wrong, so that's good. I will look at the statistics later on, and everyone that has more than 5 arrows will be thrown out of the course. Have a nice weekend.